In the last video, I've talked about how 1 Tesla can be defined in terms of the force, current, and the length. This also suggests that if suppose I have an unknown magnet and I want to measure its magnetic field, the magnetic field that's coming out from the north pole of the magnet, I can do it simply by putting that magnet close to this piece of iron rod and then measure this force. Because by measuring this force, I would be able to use this same equation to then calculate that magnetic field strength, and I would get the answer in Tesla. So that seems simple enough, but in practice, how do we actually set this thing up to measure the force? And how do we measure force anyway? Actually, we are quite familiar. I think most of us would be quite familiar with measuring force. Now, you would most likely have sometime in the past measured your own weight. Now, you measure your own weight by standing on a weighing scale. When you measure your own weight, you're actually measuring a force because your weight is the force of gravity. So the standing on a weighing scale, therefore, is one way to measure force. And in fact, this is exactly what we could use the weighing scale to measure this force. Let's see how we can do that. I would need to modify the setup a little bit to make this work. Okay, now I still need a battery. Let me put the battery there. And suppose that this is the positive pole, the battery, plus here and minus here. Now I want to connect this to the same iron rod, my long thin iron rod. Okay. That's my iron rod. Now, but this time I don't want to use two solid piece of copper. I don't want to use those solid piece of copper wire that are rigid like before. Instead, what I want to use this time, is maybe a thin and flexible copper wire. Okay, so I'm going to imagine having copper wire soldered to the two ends of the rod, here and here. So I have a flexible piece of copper wire that connect two flexible pieces of copper wires that connect the two ends of the rod, of the iron rod, to the battery. So I'm free so this rod is quite free to move up and down, left and right, because this wire is flexible. Okay, so that's what I want it to do, because it has to be free to move around if I want to measure the force that pushes this rod. Okay, so that's the plan anyway. Now, as I was saying, I can almost use a weighing scale that we take our own weight with to measure this force. But I would probably not use the exact same weighing scale, because the scale that we use to measure our own weight is usually built to measure weights that are, I don't know, maybe 50 kilograms, 100, 200 kilograms or more, depending on the range of weights that people would have. So that weighing scale is built to measure weights that might be much bigger than the force that we would get if we use a simple magnet to produce this field, and if we have a small current, because then we would expect that the magnetic force might be quite small. So what I really need is a very sensitive weighing scale. We might imagine maybe a kitchen scale that you use to measure ingredients for cooking. It would be even better if we have something more sensitive, and it's possible to buy scientific weighing scale where we can measure tiny amounts, maybe milligrams or less. So let's imagine that we have one of such scale. Okay. So let's say I have this scale, and this I put this scale under the iron rod. So that's sort of the surface of that scale, and the scale would be okay, let's say maybe it has a certain body that contains some electronic sensor that measures weight. Okay, try to draw that carefully. So there's some kind of a box that contains all the measuring components. Okay, and on the rod, I might imagine that this is a sensitive electronic weighing scale, and on the screen here there would be maybe a digital scale that would tell me the weight of this rod. Okay, that would tell me the weight of this rod, but there would usually be a button there, hopefully, where I can use to zero the balance. And zero the balance just means that if there's such a button, when I press it, then it will just show 0.000 down here, maybe in grams or milligrams. Okay, right. And this just means that even though this has a weight, even though there's some weight on the weighing scale, the scale will just measure additional weight that you put on it, and then it will show the value of the additional weight. All right, so let's say we have all this set up now, and there's the current flowing through from the battery. How can I now measure the force from a magnetic field? Okay, let's have a go at this. Suppose now that I have a piece of magnet. I bring this magnet close by. Okay, that's my magnet. Now this is an unknown, a magnet with unknown magnetic field strength. Okay, so right, suppose that this is a north pole That's the south pole. Okay, so we're all set now. The moment you bring this magnet here, remember that we had this current. We have this current flowing, okay, flowing through here. Let's say there's a current of say 0.1 ampere. Okay, that's how we set it up. And let's say the length of the wire. The length of the wire is maybe 10 centimeters. 10 centimeters, that's the length of this wire. Now the magnetic field would go through the wire, just spread out around the wire. Okay, now and right, there might be a problem here because remember I was hoping to use the formula B equals to F equals to V I L, right? What I'm hoping to do is by measuring F, I, and L to calculate the B. But remember that this setup, this equation only works when I have a uniform magnetic field for that covers the length of the wire, at least the length of the part that contains the current. Now, as I've drawn this, the field is obviously not uniform. The field is not uniform. So what should I do? Right? What I could do is I can shorten the wire so that the wire is quite short. Okay. Now let me try and do that. Okay, so it's important that when you do an experiment, it's important that you set everything up correctly. So let me remove this bit of the wire. Remove this bit of the wire, and let me reconnect the wire. I'm going to reconnect the wire so that it only connects to the part where the magnetic field is uniform. Okay. Now we have to be a bit careful about insulation here. In this case, I would mention that the wires can be all of the wires can be insulated, right? Except of course where you have the connection. But the wire can be insulated from the surrounding, from the table and from the weighing scale if necessary, because the magnetic field will just go right through any plastic insulation. Okay, so we don't need the wires to be bare, unlike the experiment in the previous few videos. Okay, so in any case, I need to make sure if I want to use that formula, F equals to VIL. If I want to use this formula, I need to make sure that the magnetic field in this region where the current flows is uniform. Okay, so actually there will be no current here actually. Okay, let me clear that part up as well. Okay, it's a bit troublesome to get an experiment right, if you have ever tried one. Okay, that's fine now. Just clear this part up as well. Okay, I think we are all set. Okay, so let's start again. Now the magnetic field. Okay, the magnetic field. I would probably want this to bring this quite close to this, so that the curved part of the magnetic field, the non-uniform part, don't spread over it too much. Okay, so the magnetic field will will go over this part of the current. Okay, so hopefully it'll still be quite uniform. It'll be quite uniform in this short bit of the wire, and okay, further away, of course, it'll start bending and become non-uniform. Okay, but let's hope that the uniform part is good enough for this experiment. If you actually set up this experiment, it's a matter of trial and error to get it right. Okay, so I have a magnetic field, and this magnetic field is unknown. Okay, and I would like to find this field. So the field is in this direction. The field is pointing along this direction. Now the current is going in this direction. Okay, so I have a current going in this direction. That's the current. That's the current here. And the magnetic field is the blue color. Magnetic field is going in this direction. Then what is the direction of the force? Now remember Fleming's left hand law. Okay, if you take out your left hand, if you like, pause the video for a few seconds and see if you can get this right. Take out your left hand, right? Point your fingers in the direction you need for Fleming's left hand law. Remember, the first finger points forward, not the middle finger. Okay, right, so let's see. The first finger points in the direction of the field. The middle finger points in the direction of the current. Therefore, what would be the direction of the force? The direction of the force would be downwards. Direction of the force would be downwards. Okay, the currents would be in this direction. That's the current, and the magnetic field is in this direction. Okay, so Fleming's left hand law will tell us that the field in this direction, first finger, current in this direction, my middle finger, then my thumb, the thumb of my left hand would point downwards. Therefore, the force is in a downward direction. Now, I purposely set this up, actually, before I started this video, so that the force will point downwards instead of upwards. Now, why would I do that? The reason is quite simple. This is a weighing balance, a weighing scale, so that measures weights, that is normally used to measure weights, which is downward. So in order to use it, therefore, it can only measure forces that are pointing downwards. So which is why I set this up so that the force would point downwards. Okay, for example, if I had turned the battery around, right, if I connected the wires the other way around, then the current would be in the reverse direction and the force would be up. The force would be up, and then it would be a bit more tricky to use the weighing scale. It's possible that a digital scale will show a negative reading when we do that. So it might work as well. But okay, in any case, these are just something that we worry about if we actually set up an experiment. Okay, so let's see. So we have this all set up now, right? So suppose that I can now take the reading, right? The moment I put a magnet here, and the magnetic field goes over the current, this would register a reading on the digital scale. Okay. Now suppose that the reading says maybe 1. Let's say it was 0.1. Let's say the unit is grams, 0.1 grams. Okay, so a very small weight that it has registered. Now, if it says 0.1 grams here, right? Assuming that maybe this is a very sensitive chemical balance, balance to measure tiny amounts of chemical substances, for example. So it would measure a 0.1 gram here, but in order to use this formula, we really need the weight in newtons. So let me do some quick conversion, maybe at a corner here. Okay, 0.1 gram. 0.1 gram is 0.1 over 1000 kilogram. Okay, and because W is equal to mg, because this assumes that it's reading a mass. So to convert it to weight, I would use weight is equal to mass times g. This would give, okay, this would give the force. This force, this is a magnetic force that's pretending to be a weight down here. So this force is then the weight, and the mass is this one. That's my effective mass. That's what the weighing scale thinks is a mass, is a weight. So it's 0.1 over 1000. 0.1 over 1000, that's the mass, times g. Okay, g is, let's see. Now what I'm going to do is I just want to illustrate this point, so I'm going to take an approximate value. I'm going to take g as roughly 10. Okay, just for example. Okay, then my answer would be 1 over 1000, 0.001 newtons. So that's the force. That is the force that I have just measured. Okay, so we now have the force. Now the force. We want to find the field. We know the current, assuming I have maybe an ammeter here, connected maybe somewhere here, that measures the current. And the length, was I sort of connected this wire myself, so I can use a ruler to measure the length. And oh yeah, well, I did mention that I want a length of 10 cm just now. Okay, so that's the length here, the length of 10 cm. So it gets a bit crowded down there. Okay, so we are more that's my L. So we have everything that we need to calculate B. So let's do it. B therefore is equal to, rearrange this, IL to the divide both sides by ILs. So B is equal to force over IL. And force is 0.001 Newton. I is 0.1 ampere. L 10 cm. 10 cm is 0.1 meter times 0.1 of a meter. And the answer is is 0.1 Tesla. Okay, so we have just done our first magnetic field strength measurements.